Now we consider the deadbeat response. If you have a system x at k plus 1 equal to jx at k and y k equal to cx at k, the observer of the system x hat at k plus 1 is equal to jx hat at k plus l x hat at k minus y at k. The error of the observable is x hat at k minus the real x at k. Then the dynamic of observation error ek plus 1 is equal to j plus lc ek. Just very easy, you substitute this one by the formula of here, x k you can substitute by this. Then you can find the ek plus 1. From ek plus 1 you can find the ek is equal to j plus lck is 0, and to have a en equal to the 0 or ek equal to the 0, j plus lc must be nilpotent. That means j plus lc power n is equal to 0. Okay. To obtain the deadbeat response for observation error, all of the eigenvalue of observation error dynamic should be equal to 0. If all of the eigenvalue of the j plus lc are chosen equal to the 0, then there exists of the change of a basic p such as this matrix. P inverse of the j plus lcp, it will be equal to this, and this equal to n. And now this, if you power n, you can extend that the p inverse about g plus lc power n, p is equal to n power n. This one is equal to 0. Then this should be is equal to 0. That we saw the here g plus lc n power 0, or we prove this one is equal to 0. Example, consider you have this system, the g is equal to and c is equal, find the gain of the L to have a deadbeat response for observation error dynamic. Is this one easy? You can find the observation is equal to here, then the ek plus 1 g plus lc ek, and the ek equal to observation error become the x hat a k minus x a k. L transpose, that means L1 and L2 is easily, you can find the zi minus j minus lc is equal to, just only extend about the defined determination here, this one is equal to deadbeat response. Deadbeat response, that means pole equal to the 0 is z2. If equal to this one equal to the z2, you can find the L1, we don't have any coefficient about L1 is equal to 0, minus 1 minus L2 equal to the 0, we can find the L1 and L2. And you can check the G plus LC power 2 is equal to 0, 100%. Pole placement plus observation design. If you saw together, if I draw all both systems together, you can find this. I can say this is my system with the input and the output state feedback. You can find the observable, and if Rk equal to the 0 with the gain of the k, you can find the uak. This is the observable and the controllable. You can find the k and the l. And here there's a question, what happens if the estimate state x hat is used in the feedback instead of the exact state? Then if you see here, I use the feedback of the x hat a k, here become minus x hat a k, and the uak will be minus x hat a k k. Now consider you have this system, define the following observations. Equation is the x hat a k, and design the feedback uak equal to minus k x hat a k. Then the dynamic observation error, that means UAK become x hat a k minus zk, and the ek plus 1 will be easily, you can find the j minus h a k x a k minus h k e a k if you substitute the system. By the dynamic of the system, you can find x a k plus 1 j minus h k x a k minus h k e a k. And if you put in the matrix x k plus 1 and e k plus 1, you can find a j minus h a k, because here multiply x a k minus h a k, and the e k plus 1 is the first one is will be x a k is a 0, and another one become j plus l c for the e a k. And you can find xk plus 1 and ek plus 1. Sorry, this one I must modify that ek plus 1 is equal to j plus lc. This one we saw the previous slide, the ek. This is for the xk plus 1. Okay, then you can find the xk plus 1 and ek plus 1 j minus hk and etc. Separation principle. If a stable observer L and stable state feedback K are designed for a linear time invariant system LTI, then the combined observe and the feedback will be stable. This principle is not true for the nonlinear system, and usually the dynamic of the observer is chosen faster than the dynamic of the controller, normally 10 times. And true for the continuous time LTI system as well. They give the one example: design a control that will place the 3 closed loop poles in -0 point and the observer that will have the deadbeat response. They give us the G, they give us the H, they give us the C, give the expression of the output feedback. Okay, we have the Z equal to, you have the 3 poles, you can put the 3 poles equal to extend about this equation, then easily you can find the K by the previous slide. Find the formula. K is a find out. Then this, that means Zi minus G plus LC should have a deadbeat response. To find it here, you can find the L1 and L2 and L3. That means this is the use the separation principle. You can find the K and you can find the L. The output feedback, if you remember, UAK will be equal to minus kx hat a k, and where the observer is defined by the x hat a k, something like this formula, with the k equal to this and the L equal to this. Here we will close the observable and controllable design, and we solve some exercise in the next slide.